An F-15 Eagle, 19 meters long, twin engines, a 13-meter wingspan, appears on a modern air defense radar as approximately 25 square meters of reflective surface. At that size, a capable ground-based radar system can detect it from around 200 kilometers away, track it continuously, and hand off a fire control solution to a surface-to-air missile long before the aircraft is close enough to threaten anything. An F-22 Raptor is roughly the same size, same length, similar wingspan, similar weight, same speeds. It appears on the same radar as approximately 0.0001 square meters, the radar equivalent of a marble. One of these aircraft can be seen, tracked, and killed before the pilot knows he has been detected. The other arrives over its target before the radar operator has finished deciding whether he is looking at an aircraft or a bird. They are separated by one number. This video is about how that number is engineered. 3 different systems working simultaneously, each attacking a different part of the same problem. And it is about the one night in 1999 when an obsolete Soviet radar system found a way through. Radar works by transmitting a pulse of electromagnetic energy in a given direction, then listening for any energy that bounces back to the receiver. The amount of energy that returns from a target, the strength of the echo, is what tells the radar whether something is there, how far away it is, and what direction it is moving. Radar cross-section, or RCS, is the number that quantifies how strong that echo is. Specifically, it describes the equivalent area of a perfectly reflective metal sphere that would return the same energy to the radar as the actual target. If a target has an RCS of 10 square meters, it produces the same radar echo as a perfectly reflective sphere with a 10 square meter cross-section, a ball roughly 3.5 meters in diameter. The actual physical size of the target is irrelevant to its RCS. What matters is how much radar energy it captures and how much of that energy it reflects back toward the radar receiver. Shape dominates this calculation. A large flat surface, like the vertical tail of a conventional fighter, oriented perpendicular to an incoming radar beam, reflects energy back toward the transmitter very efficiently. A curved surface scatters energy in multiple directions, spreading the return signal widely and reducing the amount that reaches the receiver. An angled surface redirects energy away from the transmitter entirely. The material of the surface matters too. A metallic surface reflects almost all incident radar energy, while certain materials can absorb it and convert it to heat. Stealth design is the engineering of both of these properties simultaneously. Shape the aircraft to redirect returns away from threat radars, and code it to absorb what cannot be redirected. The relationship between radar cross-section and detection range is one of the most important and least intuitive facts in stealth engineering. Detection range does not scale linearly with RCS. It scales with the 4th root of RCS. To cut the detection range of an aircraft in half, you do not halve its RCS. You reduce it by a factor of 16. To cut detection range to 1/10, you reduce RCS by a factor of 10,000. This sounds like enormously difficult engineering, and it is. But it also means that once you achieve that 10,000-fold reduction, the payoff is dramatic. An air defense radar designed to detect a conventional fighter at 200 kilometers will detect an F-22 at around 20 kilometers, if it can detect it at all. At 1,000 kilometers per hour, the F-22 covers 20 kilometers in about 72 seconds. That is the window in which a radar system must detect the aircraft, classify it, hand off a fire control solution, and launch a missile with enough time for it to reach intercept. At 200 kilometers, that process has minutes. At 20 kilometers, it has just over a minute. and modern air defense radars are not always monitoring the right frequency range to find a stealth aircraft at any range. To put the RCS numbers in context, a conventional fighter like the F-15 Eagle has an RCS of roughly 25 square meters from the front. The F-16 Fighting Falcon is around 5 square meters. A man standing in a field has an RCS of approximately 1 square meter. The F-117 Nighthawk, the first operational stealth aircraft with its faceted angular design, reduced that number to roughly 0.003 square meters, the size of a hummingbird. The F-22 Raptor, with more advanced shaping and materials, gets to approximately 0.0001 square meters from the front aspect. The B-2 Spirit stealth bomber, designed at similar fidelity to the F-22, reaches the same threshold, 0.0001 square meters, a marble on radar at any frontal aspect. A 21-meter flying wing that weighs 170,000 kilograms, appearing on radar as an object with the reflective signature of a glass marble. The shaping of a stealth aircraft is not aesthetic. Every geometric decision, the sweep angle of the wings, the angle of the vertical tails, the shape of the inlet lips, the orientation of access panel edges, the sawtooth pattern on the canopy frame, is made to control exactly where radar energy goes when it hits the aircraft's surface. A conventional aircraft, like the F-15, has wing leading edges swept at one angle, trailing edges at a different angle, vertical tails at a third angle, horizontal stabilizers at a fourth. When a radar beam hits it from any given direction, energy reflects back across many different angles simultaneously. Some back toward the radar, some off to the side, some forward. This creates a radar return that is present across a wide range of angles and viewing aspects. The radar sees something from almost everywhere. The F-22 uses a design philosophy called planform alignment. Every primary hard edge on the aircraft, the wing's leading edge, its trailing edge, the leading and trailing edges of the horizontal stabilizers, the front edges of the canted vertical tails, the lips of the engine inlets, the edges of access panels, weapons bay doors, the canopy frame seam, is swept to the same angle. On the F-22, that angle is 42 degrees. Every edge on the aircraft responds to an incoming radar beam the same way, because they are all oriented identically. Instead of scattering energy in many directions at once, the aircraft concentrates any radar return into a small number of narrow, predictable angular spikes, and orients those spikes away from where threat radars are likely to be. There is a secondary element to this. All panel breaks, which are unavoidable on any real aircraft, use sawtooth edges rather than straight cuts. The canopy seam, weapons bay doors, landing gear covers, and every access panel has a serrated, angled edge rather than a straight one. A straight panel edge perpendicular to the aircraft's axis of flight would produce a radar return directly forward, into the likely threat envelope. A sawtoothed edge aligned with the planform angle redirects that return to the same narrow spikes as every other edge on the aircraft. The aircraft is uniform in its angular strategy from nose to tail. There is no weak seam where a differently angled surface undoes the rest. If you look at the air intake of a non-stealth jet fighter straight on, you are looking directly at the front face of the engine compressor, a series of spinning metal blades arranged in tight concentric rings, angled toward you, reflective, and rotating. This is one of the single strongest radar reflectors on any aircraft. The engine face of an F-15 or an F-16, viewed from the front, contributes a large fraction of the aircraft's total RCS. It is, in radar terms, a cavity that captures incoming energy, bounces it around its metallic interior, and returns a strong signal. The F-22 eliminates this entirely by making it physically impossible for any radar wave to travel a straight path from the intake opening to the engine face. The inlet duct is shaped as a serpentine curve, an S-bend, with enough offset that no straight line exists from the intake opening to the compressor blades. A radar wave entering the inlet strikes the curved duct wall, reflects internally, strikes another surface, reflects again, and dissipates. The duct interior is coated with radar-absorbing material to weaken each successive reflection. By the time any residual radar energy could theoretically reach the engine face, it has bounced multiple times off ram-coated surfaces and lost most of its original amplitude. The return signal that makes it back out of the inlet is negligible. This is not a trivial engineering achievement. An S-bend inlet duct must still deliver the airflow the engine needs at all flight regimes, including supersonic speeds, hard maneuvers, and varying angles of attack, without introducing turbulence or pressure distortion that the compressor cannot handle. The aerodynamic and the stealth requirements are in direct tension. Designing an S-duct that satisfies both simultaneously was one of the most significant engineering challenges in the F-22's development. Shape alone, even executed as precisely as the F-22's geometry, cannot reduce RCS to the levels required. There are surfaces on any aircraft where the geometry cannot be arranged to redirect all radar energy away from threats. Panel joints, canopy frames, areas where aerodynamic requirements and stealth requirements conflict. These surfaces are handled with radar-absorbing material, a coating that does not reflect radar energy but absorbs it. The primary ram used on modern stealth aircraft is iron ball paint. It contains millions of microscopic spheres, each coated with carbonyl iron or ferrite, suspended in an epoxy carrier. The spheres are typically a few micrometers in diameter, smaller than a human red blood cell, and distributed uniformly through the paint at a precisely controlled density. They are electrically isolated from each other. Each sphere is an independent particle, not part of a conductive network. When a radar wave, a pulse of oscillating electromagnetic energy at a specific frequency, strikes a surface coated with iron ball paint, the alternating magnetic component of the wave interacts with the ferromagnetic material in the carbonyl iron coating. The iron atoms respond to the alternating field by oscillating at the wave's frequency. Those molecular oscillations dissipate energy as heat, the same fundamental mechanism by which a microwave oven heats food, applied at a very different scale and frequency. The radar energy is absorbed by the coating, converted to a tiny amount of heat, conducted into the airframe, and dissipated. The reflected signal from that surface is dramatically weaker than it would be from bare metal. The composition of the paint is calibrated to the specific radar frequencies it needs to absorb. A material optimized for X-band radar, around 8 to 12 GHz, the frequency range of most modern fighter and fire control radars, uses particle sizes and densities tuned to resonate at those frequencies. The full formulations are classified, but the principle, ferromagnetic particles resonating in response to radar's alternating electromagnetic field, converting energy to heat, is physics that has been understood for decades. The engineering is in the precision of the tuning. The F-117 Nighthawk was the first aircraft in history designed from the outset around stealth principles. Its faceted, angular shape, so aerodynamically peculiar that it required a fly-by-wire computer to remain stable, was designed before the computing power existed to model complex curved surfaces. The facets redirected radar energy in specific directions away from threat radars. It worked. In January and February of 1991, during Operation Desert Storm, 36 F-117s flew approximately 1,300 sorties over the most heavily defended airspace in the world at the time. The perimeter of Baghdad was defended by an integrated network of radar systems, surface-to-air missiles, and anti-aircraft guns that made it effectively suicidal for any conventional aircraft to penetrate. The F-117s flew through it repeatedly, at night, without a single aircraft lost. They attacked 1,600 high-value targets and delivered a significant fraction of the precision strikes against hardened command and control infrastructure in downtown Baghdad. The aircraft was never definitively acquired by Iraqi radar during the entire campaign. Stealth was not a concept anymore. It was a proven operational reality. On the night of March 27, 1999, during NATO's air campaign over the former Yugoslavia, an F-117 Nighthawk with call sign Vega 31 was acquired by a Yugoslav surface-to-air missile battery and shot down. It was the first, and to date, the only stealth aircraft ever destroyed in combat. The F-117's stealth design was optimized specifically for X-band radar, the high-frequency, high-resolution band used by modern fighter radars and most modern fire control systems. The S-125 missile system used by Colonel Zoltan Dani's battalion operated at a much lower frequency. The P-18 early warning radar that detected Vega 31 used a longer wavelength that interacted with the F-117's geometry differently. At lower frequencies, the faceted shaping that was highly effective against X-band radar produced a larger return. The aircraft's RCS advantage was smaller at this frequency, and the target was detectable at closer ranges than the pilot expected. But the frequency was only part of the equation. Dani made two additional decisions that were tactically decisive. First, his radar operators used their transmitter in short, controlled bursts, approximately 17 seconds of radiation at a time, to avoid detection by the NATO aircraft hunting for radar emissions. A radar that transmits for 17 seconds is extremely difficult for passive anti-radiation systems to locate and target. Second, Dani had intelligence about the F-117's flight path. NATO had been flying the same general approach corridors on predictable schedules. On the night of the shootdown, Vega 31 had just completed its bomb drop, meaning its weapons bay doors, which were normally closed and contributed to the aircraft's low RCS, had been open. An open weapons bay significantly increases radar cross-section. The aircraft's stealth geometry was temporarily compromised at the moment it was in the engagement envelope of a system using a frequency it was not optimized against. The shootdown was not proof that stealth doesn't work. It was proof that stealth is not invisibility. It is a specific frequency-dependent, geometry-dependent reduction in detectability that holds as long as the tactical conditions that the engineering assumed remain in force. Change the frequency, change the flight path predictability, or open the weapons bay doors at the wrong moment, and the RCS margin narrows. The engineering defines the baseline. The tactics determine whether that baseline is sufficient. The F-22 is not vulnerable to the same frequency gap. Its curved surfaces and more refined shaping are effective across a broader frequency range than the F-117's facets. But the underlying principle, that stealth is a contest between specific engineering choices and specific counter-engineering choices, has not changed. Planform alignment. Every edge on the aircraft swept to 42 degrees, concentrating radar returns into narrow, controlled spikes aimed away from threat receivers. A serpentine inlet duct that makes direct line of sight to the compressor face geometrically impossible, forcing any radar energy that enters the intake through a series of ram-coated internal reflections until it is too weak to generate a meaningful return. Iron ball paint. Millions of carbonyl iron spheres resonating in response to radar's alternating electromagnetic field, converting the wave's energy into heat rather than reflecting it back as signal. 3 systems applied simultaneously to a surface area of roughly 80 square meters of aircraft, producing a radar cross-section of 0.0001 square meters. The marble is not magic. It is physics, manufacturing precision, and geometry, applied to every panel, every edge, every seam, at a level of detail most people will never see.